Hello everybody, JT's Physics of Cycling video number 7, bringing it all back into the real world. Okay, so let's imagine some scenarios that we want to cancel out. Let's say that a rider is riding along a time trial course like this, and he's got ups and downs. He has to work really hard going up, and he gets that back going down and all that kind of stuff. We're going to cancel that out. And also wind patterns. Let's say the rider is, this is the rider here, and he is heading in this direction. He could have winds in a multiple, in a variety of directions. He can have a direct tailwind or a direct headwind, or a variety of crosswinds. So we are going to assume, for the sake of this next lesson, that there is no grade over the course of the time trial, and that there is no wind. The resistance that the rider is experiencing is going to be only because of his own velocity. And there's a lot of data on the internet regarding wind tunnel studies and things like that, with aerodynamic design, and we've got some pretty good models. Let's create a coordinate system here, and let's say that this is the power opposing, so it's POSE, opposing the rider, and that this is the rider's velocity. And we all know that the faster we go, okay, the force of air becomes greater and greater. I mean, that's pretty easy to understand. We can all go to 20, 25, 30 miles an hour. And then we begin to experience a force that's going to resist us, and we're going to reach a terminal velocity. But what are those models? How do they behave mathematically? And I've been able to find on the internet some models, and I have condensed these models, and they are not time trial bike design, they're not aero helmet design, they're not aero clothing designed, but they are just an average. I've taken averages from several different sites, and the equation is the resistance, or the power, okay, working against you on your bicycle as you move through still air and no grade, is equal to, and I have this here, 0.0106 times the rider's velocity, and then that raised to the 3.03 power. So what does that mean? That means that you know, as we increase our speed, the power, okay, this is the power acting against us, and this is our velocity. We know that that's going to do something like this. And we will reach a maximum power, whether it be, say, 400 watts or 500 watts, or even 600 watts for some of the pros. But this is the function here. This is the function that is the best average. For an average geometry of the bicycle and the bicycle rider, the average clothing that he's riding in, and so if you want to compute the power that is acting against you as you ride on a road bike, we need to specify that. then the function it appears to be, a good average, is the 0.0106 times the velocity that you're moving through the air, and that number raised to the 3.03 power. So this this equation right here is not derived from physics. I mean, we've been through the physics of cycling, but experimentally, these numbers, these coefficients and exponents have been derived experimentally. So if you want an idea of the wattage that is working against you, then this is the equation you need to use. And I will just give you an example. We all know that we reach a point where we can't go any faster, that the air resistance, the power against us, is preventing us from going any faster. So I've got this graph. I'm going to try to hold this up and show you the graph. There's the graph going off. This axis is the rider's velocity, and this axis would be the power acting against. And we can go in here to a table, and at this says that at 30 miles an hour there's about 315 watts of power acting against us. And then we just go up to 35, and then we're at 505 watts. Okay, so you can see that's exponential. At 30 miles per hour, our power resistive was 315, but at 35 miles per hour, the force resistive was 505. And I'm not real up to date on the power wattage outputage, what a rider can sustain, but I would imagine that it's well, I'm not going to imagine anything because I'm not educated on that. Riders on my team are. But if you imagine that you do have a ceiling, you have a maximum power output, and we're using watts, but another way is horsepower, that you're actually, the graph, I'm sorry, let me draw a better graph. Let's call this power, and let's call this velocity into still air and with no grade. It's going to go up, but then we're going to reach an asymptote. We're going to reach a point at which the human being cannot exceed. So that is the functionality, mathematical functionality of our speed into still air with no terrain. You want to add terrain, then it's going to get very complicated. But this is the behavior. So the point is, anything that you can do, I mean, anything whatsoever that you can do to to reduce your aerodynamic drag, okay? So you are going to be moving into air. If you streamline yourself, if you tuck your shoes in, if you have disc wheels, if you're in an aero helmet, all of these things are going to give you back power. And that's going to allow you to have a higher velocity. And of course, the professionals know this. But I'm doing this for my team and my club, and so don't ever wear loose clothing, and always tuck your shoestrings in when you can. Alright, well, that's the first model. And for those of you that are mathematically inclined and want to see that model again, the power against a rider on average is 0.0106 times your velocity raised to 3.30 or 303 power. So you can calculate the power. All you have to do is enter your velocity in miles per hour, and it's all been converted. All the conversions are good. And this power output would be in watts. So if you know that you can sustain a wattage of 250 watts for 25 minutes, then you can reverse this and solve that for V. So anyway, there you go. That's video number 7. And I'm not having much feedback, so I'm assuming that these videos are a little bit stupid. Maybe not, but if you're finding any interesting information from these, please let me know, and then I'll keep going. Thank you very much.